And this afternoon, in this conference, the last presentation will be given by the Merve Elmadi from the Central Metallurgical Research and Development Institute, Egypt. And she's gonna explain us the effect of polypropylene grafted p-hydoxy-N-phenyl maleimide comptablizier and organoclay percent of the properties of polypropylene organoclay nanocomposites.
Good evening, everyone. My name is Marwa Eid Abdelaziz Mohammed. I am a researcher assistant at the Central Metallurgical Research and Development Institute, Advanced Materials Division, Composite Materials Lab in Cairo, Egypt. My presentation is entitled Effect of Polypropylene Grafted Para-hydroxy-N-phenyl Maleimide Comptablizier and Organoclay percent on the properties of polypropylene organoclay nanocomposites. First of all, thank you very much for your attendance, and I hope you will enjoy my presentation, through which we will see how a very small amount of a nano-sized material can act as a building block to create and construct new materials with unexpected properties. The outlines of my presentation will be introduction, supplemental, results and discussion, which is divided into 3 parts. The first part is about the organic modification of clay. The second part is about the senses of a comptablizer, and the third part is about senses and characterization of polypropylene layered silicate nanocomposite. Finally, my conclusions. Composite. What does it mean? It means a material that is composed of 2 materials insoluble in each other, and its properties usually differs from the property of its either constituent. Any composite material is composed of 2 phases. The first phase is the matrix, which is the continuous phase, and the second phase is the reinforcement, which is the dispersed phase and is responsible for the enhancement in the properties. Usually, composite materials can be classified according to their nature to natural, traditional, and sensitive, and they may be also classified according to the kind of reinforcement to particle fiber or fiber sheets stuck to each other to give a structural composite. Also, they may be classified according to the matrix to metal matrix composite, ceramic matrix composite, and polymer matrix composite. Nanocomposites. They are a new class of materials which have at least one dimension of at least one of its constituents in the nanometer scale. The added nano reinforcement may be 3-dimensional, such as spherical alumina nanoparticles, 2-dimensional, such as carbon nanotubes, and 1-dimensional, such as sodium montmorillonite mineral clay. Usually, the properties of the nanocomposites is enhanced than the individual components due to the high surface area to volume ratio, and their properties depend on both the matrix and reinforcement material, the amount of added reinforcement, and the geometry of the nano reinforcement, its shape, size, distribution, and orientation. In our study, the prepared nanocomposites will be called polypropylene layer silicates nanocomposite, in which the matrix is polypropylene polymer while the reinforcement is layer silicate. Why we choose polypropylene especially? Because it is light in weight, low in cost, it has high window processing temperature, and at room temperature it is almost resistant to all organic solvents. And the reinforcement added in our study is layer silicate, which is one member of smectite clay family, and it belongs to the structural family known as 2-to-1 phyllosilicate. Each clay particle is composed of hundreds or thousands of layers stuck to each other, and they are by weak van der Waals forces, and they are separated by interlayer spacing containing exchangeable earth cations. In order, the thickness of each layer is about 1 nanometer. To obtain the nano-sized layer silicate, we have to separate these layers from each other. Method of synthesis of polymer layer silicate nanocomposite. There are 3 possible methods. The first method is the solution intercalation, in which the polymer is dispersed in the appropriate solvent. Then the layer silicate is dispersed in the same solution. This solvent causing swelling of the silicate layers, allowing the polymer to diffuse between these layers to form the polymer layer silicate nanocomposite. The second mechanism is in situ intercalated polymerization, in which layered silicate is dispersed in the monomer solution, and by adding the initiator, the polymerization process takes place between the clay layers, leading to the formation of a polymer layer silicate nanostructure. Finally, melt mixing intercalation, which is the most favorable method, and it is the most used method in industry, in which layer silicate is mixed with the polymer in its molten state, and then by extrusion or by applying a shear force, these layers are separated from each other, allowing the polymer to diffuse between them and forming polymer layer silicate structure. There are three possible structures of the formed polymer layer silicate. The first structure is the conventional composite, in which layered silicate are dispersed within the polymer matrix, stuck to each other. The second possible structure is the intercalated nanocomposite, in which some amount of polymer chains diffuses between the clay layers, separating these layers to some extent, but still they are bonded to each other. The third structure, which is the most favorable structure and the one which has a great enhancement in the properties, is the exfoliated nanocomposite, in which layer silicate are dispersed within the polymer matrix, separated from each other. The aim of our work was how to overcome the problem of hydrophobic polypropylene, of incompatibility between the hydrophobic polypropylene and the hydrophilic clay. To obtain polypropylene layer silicate exfoliated structure with enhanced properties. This problem was overcome by organic modification of clay and by synthesis of a comptablizier. Our experimental work is divided into three parts. The first part is the modification of clay, which was carried out by cation exchange reaction, in which long alkyl chain surfactant exchanges the interlayer earth cations, leading to increase the space between the layers, making them more hydrophobic and more compatible with the polymer. Two different organic surfactants were used. The first one is hexadecyl trimethyl ammonium bromide, and the second one is tributyl hexadecyl phosphonium bromide. We used two different apparatus in the modification process: the usually used magnetic stirrer and the high-speed mixer, which is used for the first time in the modification. Results and discussion. XRD analysis shows that the value of despacing in case of the montmorillonite clay without any modification was found to be 13.3. But by modification using the high-speed mixer, the values increases to reach 27.3 and 27.7. While the modification using the magnetic stirrer increases the value to 19.2 and 18.55. From this, we can conclude that the modification using the high-speed mixer causes greater value of despacing. To study the effect of mixing time in the high-speed mixer, 5 different experiments were conducted at different 5 times. Half hour, 1, 1.5, 2, and 2.5 hours. And it was found that the maximum despacing value was obtained after 1.5 hours steering in the high-speed mixer. Infrared spectroscopy shows that for the modified clay sample, 2 new peaks appeared in the 2 modified clay samples. These 2 peaks were ascribed to be due to the CH asymmetric and symmetric stretching vibration of the long alkyl chain present in the 2 surfactants. Thermogravimetric analysis showed that the decomposition of the clay takes place in only 2 steps. The first step is at 67, which is due to the dehydration of the water, and the second step was at 465 due to the removal of the structural hydroxyl group. While for the 2 modified clay samples, the decomposition takes place in 4 steps. For the 2 modified samples, the first step is due to the removal of water, the second step is due to the dehydration of the interlayer earth cations, the third step is due to the removal of the surfactant, and finally the fourth step is due to the removal of the hydroxyl groups. The scanning electron microscope of the modified clay sample shows a massive thin layer structure with some interlayer spaces, which improves the modification process. Also, transmission electron microscope shows that there is a particles of dimension of 100 nanometer, and this result proves the XRD and scanning electron microscope results. Second part of my experimental work is the synthesis of a comptablizier, which contains both a hydrophilic part and a hydrophobic part to increase the compatibility between the polymer and the layer silicate. At the first, we have to synthesize a p-hydoxy-N-phenyl maleimide monomer according to the following equation. Then, polypropylene was grafted with different weight percent of the prepared monomer in the presence of a fixed initiator percent using the melt mixing method in a twin screw extruder. The proposed reaction mechanism of the grafting reaction is as seen here. Results and discussion. The infrared spectra of pure polypropylene and polypropylene grafted samples shows the appearance of two new peaks for all the grafted polypropylene samples, and their intensity increases by increasing the amount of the added monomer, which improves the grafting reaction. Melt flow index measurements are usually used to determine the ease of flow of material and its viscosity. If the material has a high melt flow index value, this means that it will have a low viscosity and vice versa. By measuring the melt flow index for all the prepared sample and for pure polypropylene, we have seen that the value of melt flow index increases greatly by grafting of polypropylene with 1% of p-hydoxy-N-phenyl maleimide monomer. Why? Because at this low concentration of the monomer, most of the free radicals will interact with the polymer itself, leading to the degradation of each chains, decreasing their molecular weight, decreasing their viscosity, and hence increasing their flow rate. But by increasing the amount of the added monomer, the value of the melt flow index decreases again. The polarity of pure polypropylene and polypropylene grafted samples were measured by measuring the contact angle of distilled water on the surface of the prepared sample. It was found that the contact angle decreases by increasing the amount of p-hydoxy-N-phenyl maleimide monomer, which means that the hydrophilic character increases. But by increasing the amount of monomer to 4%, the contact angle decreases again. This may be due to the non-homogeneous distribution of the grafted chains on the surface. Thermogravimetric analysis showed that there is a great increase in the thermal stability of polypropylene by grafting it with p-hydoxy-N-phenyl maleimide monomer, and the thermal stability increases by increasing the amount of added monomer. This can be seen from the increased value of the initial decomposition temperature, maximum rate of decomposition temperature, and the temperature at which half of the material decomposed. The heating and cooling curves, differential scanning calorimetric curve, shows that by grafting of polypropylene with different weight percent of p-hydoxy-N-phenyl maleimide monomers, the melting temperature decreases while the crystallization temperature increases. Also, the enthalpy of melting and the enthalpy of crystallization are not affected by the grafting reaction. All the samples are of comparable degree of crystallinity. The third part of our experimental work was the synthesis and characterization of polypropylene layer silicate nanocomposites, in which 4 series were prepared using the 2 different organically modified clays. Within the first 2 series, the amount of added organically modified clay is varied from 1 up to 7 weight percent, while the amount of added comptablizer remains fixed all over the experiments. The another 2 series are the same but in absence of a comptablizer. Results and discussion. The prepared samples were characterized using different characterization techniques such as melt flow index, differential scanning calorimetry, X-ray diffraction analysis, thermogravimetric analysis, dynamic mechanical analysis, scanning electron microscope, and permeability test. XRD results shows that for polypropylene organically modified clay 1 samples, the diffraction peak of the organically modified clay disappears from all the composite samples, which means that the clay lost its order and doesn't give any peak. This ensures that the obtained structure is an exfoliated structure. The same is for polypropylene organically modified clay 2 samples, also in presence of comptablizer. Also, in absence of comptablizer, the trend is the same. Melt flow index measurements were carried out to all the samples, and two factors were studied. The first factor is the effect of the comptablizer, and the second factor is the effect of organoclay percent. It was found that
1 minute left.
by increasing the amount of organically modified clay, the value of melt flow index increases both in presence and in absence of comptablizer. The same trend is observed for the second two series. Scanning electron micrograph shows that in case of absence of comptablizer, the surface is rough and the clay particles are present as stuck on the surface, while in case of presence of comptablizer, there is improvement in the distribution of the clay particle within the polymer matrix. The same trend is observed for the second two series. Thermal analysis shows that the thermal stability increases by increasing the amount of added organically modified clay. Differential scanning calorimetry shows that the melting temperature decreases while the crystallization temperature increases for all the prepared samples. Dynamic mechanical analysis test is used to study the viscoelastic behavior of the material at the complex modulus equals the sum of the storage modulus and the loss modulus. But the ratio of the loss modulus to the storage modulus equal to the damping coefficient, and it represents if it is greater than 1. This means that the viscous part of the material is the one which determines its characteristics. From this, we can see that by plotting the modulus versus temperature and the damping coefficient versus temperature, we can see that the sample which have a comptablizer is the one which has the highest value of storage modulus and the lowest value of damping coefficient. The same is observed for all the prepared samples. Barrier properties. For a material to be used in packaging application, it must have barrier properties. But for a polymer, its barrier properties are very bad because it has high permeability for gas molecules and water vapor molecules. In case of polymer clay nanocomposite, the path of the gas molecules and water molecules will be more difficult through the composite structure. By measuring the water vapor transmission rate, we can see that by increasing the amount of organically modified clay, the water vapor transmission rate decreases. The same is observed for the second series. Oxygen transmission rate also decreases by increasing the amount of organically modified clay in all the prepared series. Conclusions. Egyptian clay called multimorronite was successfully modified with two different organic surfactants, hexadecyl trimethyl ammonium bromide and tributyl hexadecyl phosphonium bromide. XRD results of the modified sample show the value of basal spacing in case of modification using high-speed mixer are greater than the magnetic stirrer. Thermogravimetric analysis showed that both organoclays are more thermally stable than multimorronite clay itself. Both scanning electron microscope and transmission electron microscope confirmed that organic modification of clay causes an increase in the basal spacing value between the layers. Polypropylene was successfully grafted with various amount of p-hydoxy-N-phenyl maleimide monomer. Melt flow index results show that the grafting of polypropylene sample exhibit high melt flow index compared with the net polypropylene. The contact angle of the grafted polypropylene samples gradually decreases with p-hydroxy-N-phenyl maleimide content up to 3%. TGA results show that the thermal stability is enhanced upon the incorporation of p-hydroxy-N-phenyl maleimide grafted chains. Differential scanning calorimetric results show that the melting temperature of grafted polypropylene sample decreases while the crystallization temperature increases with increasing the extent of grafting. XRD results of the prepared composite show that the diffraction peak of the modified clay disappears from all the samples. Melt flow index shows that all the prepared samples with and without comptablizer have higher values of melt flow index than the virgin polypropylene. The scanning electron microscope micrograph displayed both smooth surface fissure for all the samples in the presence of the comptablizer and rough surface for those prepared without comptablizer. The thermogravimetric curves show that the incorporation of each kind of modified clay into polypropylene matrix lead to an increase in the thermal stability of polypropylene. Dynamic mechanical analysis results show that the prepared nanocomposites have higher value of storage modulus than that of pure polypropylene over the whole temperature range. The results of both the water vapor permeability and oxygen permeability showed that the incorporation of modified clay particles into polypropylene matrix had a significant effect on its barrier properties. Thank you.
Thank you. very heavy presentation, huge amount of characterization work, and congratulations. Very good. So we have 30 minutes for discussion, questions, comments.
Okay, I'll ask the last person first.
Sure.
So you said you are the intercalated, whatever the intercalation, the layers are going.
Intercalation of polymer between clay layers.
So what is the thickness of the layer?
Each layer is 1 nanometer. So
Yes.
if we success to separate these layers from each other, we will obtain the nanometer structure.
That's a nano. That's what we call
Each
the
layer is 1 nanometer.
I see. Okay. That's now for the second person, third. So you are using the lasers. Did you change the intensity of the laser, or always use one? The intensity means the power.
One intensity is not.
Not nothing to do with the intensity.
No change of intensity.
Oh, I see. And I have one for you too. So you are working. You are saying you are doing something for a company, right? So who will own the outcome? Say you are developing a technique.
Yeah.
So are you guys going to own that one or the company?
Now they told that they are giving partial funding.
I see.
Partial funding. Once it will succeed, they told that they will take all the things and they will give the funding to.
But they're right. Okay. That's a big problem.
For you, I think the preparation of graphene. But my question is about you trying to get the particle size by using the SEM. I think SEM is not accurate.
Yes.
Do you use the Bayeshar equation or?
Transmission electron microscope, but I haven't put it here.
Almost everything.
Okay.
All characterization.
I don't think anything left. I've never seen that many conclusions.
XRD have from the Bayeshar equation you can define the size of the particles. Okay. Also another technique, Williamson also have equations. Will get define the intermolecular space. Will get accurate then of the SEM process. First question. Second question about the modulus of elasticity. I think the modulus of elasticity complex have I missed in imaginary value is missed E dash plus I E double dash. There are not algebraic sum.
That's more technical.
You can ask again. What is that? The answer was? Your answer was just.
From the literature.
Ah, okay. More questions, comments? I have a question for you actually. You show the composite material with the CT scan results, shorter direction. So is there any limit for the type of materials for the CT scan because of the energy level of the CT, or any type of thermal set composite can be seen?
Which kind? Yeah, of course, this the limit of.
This was epoxy and the, is that epoxy and the carbon fiber?
And it was epoxy and glass fibers.
Glass
So
fibers.
we have quite good contrast in density.
It's a
So-
perfect picture. I haven't seen that much clear. It was very nice. So
yeah,
anything.
it's done by collaborators of mine which work in the synchrotron facility in
I think
Yeah, it's in
so huge energy they have then.
Yeah.
Ah, okay.
Yeah, very
So
correct.
not the lab
Yeah,
level
Not
CT.
Oh, yeah,
teaching.
that's
Okay.
No, we do, yeah, yes.
Nice.
Lab microcity are little adapted to very fine scales.
A couple
Yeah.
geometers, diameter, electron acceleration systems.
Yeah,
So
it's somewhat almost a laser X-ray beam, so it's very good.
Nice
quality.
system.
Yeah.
it's nice. Any more question? Comments? And I guess we are going to close the conference academic part now. And thank you for everyone and all the speakers that shared their knowledge with us. And congratulations again and all of them.